Electric charge has always been a matter of wonder and awe for us. Lightning always captivates human imagination. Benjamin Franklin explained that lightning is an electrical phenomenon. These brilliant streaks of light are surely the most observable manifestations of naturally produced electricity. Production of electricity, however, didn't remain a mere prerogative of nature. Humans learned to produce and use it. What happens if a person, after combing her hair, places the comb near bits of paper? The bits tend to stick to the comb. What conclusion can be drawn from this? Certainly, the comb develops a certain property that helps it to generate attractive force on the bits. In the language of science, we say that the comb gets charged. Rubbing resinous substances such as an amber rod with woolen cloth charges the rod. Lightning is a sheer interplay of electric charges. Clouds carry strong negative electric charges, while the earth carries positive charge. Electricity tends to travel between opposite charges. Therefore, negative charges from the clouds reach out to meet the positive charge on the ground, thereby causing lightning. Opposite charges in clouds can also produce lightning. Speculations did exist, but nobody quite understood the properties of electric charge until 1785. In that year, Charles Coulomb demonstrated repulsion between electric charges. Our understanding of electric charge and electrical phenomena was further enriched by Michael Faraday's research into electricity and electrolysis. In Faraday's time, it was a fashion for scientists to travel from one place to another to deliver talks on science and to demonstrate electrical discharges in glass tubes. Most of the air would be pumped out of such a glass tube and a high voltage applied across wires embedded in opposite ends. This resulted in lovely patterns inside the tubes. This entertained the audiences. It was observed that when the pressure inside such a tube was low, a pink glow filled the tube. Further decrease in pressure caused the pink glow to concentrate around the positive electrode. Correspondingly, a blue glow would get concentrated around the negative electrode. The space between the glows was found to be dark. This space is known as Faraday's dark space. Pumping out air of a glass tube wasn't, however, easy. In 1855, Heinrich Geissler, a German physicist, invented the mercury vacuum pump. With this pump, he could almost remove all the air from a sealed glass tube. Julius Plucker, a friend of Geissler, used the pump to evacuate a special kind of tube. there were two electrodes inside the tube. Plucker attached one electrode called the anode to the positive terminal of the battery. He attached the other electrode called the cathode to the negative terminal. Plucker noticed that the glass near the anode glowed with greenish light. When Plucker held a magnet near the tube, the glowing spot moved. Johann Wilhelm Hittorf, a student of Plucker, put solid objects inside the tube between the cathode and the glow. These solid objects cast shadows. Hittorf inferred that the cathode was emitting something that traveled in straight lines, just like light rays. The German scientist Eugen Goldstein named these rays as cathode rays. However, what were the cathode rays? Nobody could come up with a definite answer. William Crookes, an English scientist, thought that cathode rays were streams of molecules that had picked up a negative electric charge. He knew from the laws of electricity and magnetism that a charged particle in a magnetic field would be deflected. Since a magnetic field caused cathode rays to deflect, he reasoned that they must be made of charged particles. But if cathode rays were streams of charged particles, an electric field should also have deflected their path. Heinrich Hertz, a German physicist, tested this hypothesis. He set a cathode ray tube between two metal plates. One plate was positively charged and the other was negatively charged. As per this hypothesis, the negatively charged particles should have got attracted to the positive plate. When Hertz connected his tube to the battery, the cathode rays kept going in a straight line. He concluded that cathode rays were a new kind of electromagnetic wave. Philip Leonard, a student of Hertz, designed a cathode ray tube with a thin foil at one end. The cathode rays went right through the foil. Since gas molecules could not go through the foil, he safely concluded that the cathode rays were not charged particles. Leonard agreed with Hertz that they must be electromagnetic waves. Jean-Baptiste Perrin, a French physicist, believed that cathode rays were particles. To prove it, he designed a special cathode ray tube to catch the rays. Inside the tube, there was a metal cylinder with a slit. On turning the tube on, the cathode rays passed into the cylinder. Perrin connected the cylinder to an electroscope, an instrument that measures electric charge. The electroscope showed that the cylinder became negatively charged when cathode rays went into it. This led Perrin to conclude that cathode rays were charged particles. Leonard did not agree with Perrin's view. According to him, there might indeed be charged particles coming from the cathode, but they had nothing to do with the glow. Perrin insisted that cathode rays were waves. At the height of this controversy, J. Thomson, the famed British physicist, entered the scene. It was only by chance that Thomson became a professor of physics. As a boy, he had planned to be an engineer. As his family was unable to pay for his apprenticeship, he was forced to go to college. Thomson studied engineering, but soon realized that mathematics was closer to his heart. His professor of mathematics encouraged him to apply for a scholarship at Cambridge University. Cambridge was and still is one of the best universities in the world. Thomson never dreamt of being a student there. Thomson, however, won the scholarship on his second attempt. This was a big turning point in his life. A second turning point came in 1884 when Lord Rayleigh retired as the Cavendish Professor of Experimental Physics. Thomson, who had some experience of working with Rayleigh, applied for the job. To his utter disbelief, he got it. After taking over as Cavendish Professor, Thomson started studying the passage of electricity through gases. To find out what are cathode rays, he designed a series of experiments. He began with an experiment to show that the cathode rays were indeed carrying electric charge. Thomson set up a tube with a metal cylinder inside it, similar to the one Perrin had used. But he did not put the cylinder directly in the path of the rays. Instead, he used a magnet to deflect the rays. When the rays were not directed at the cylinder, he measured no electric charge. When they were directed into the cylinder with the help of a magnet, Thomson found that the cylinder was charged. He concluded that whatever carried the negative charge always followed the path of the rays. Next, Thomson wanted to show that a pair of electrically charged plates did indeed deflect the path of the cathode rays. From his work with gases, he knew that when the cathode rays passed through a gas, the gas molecules became electrically charged. Consequently, positively charged molecules drifted toward the negative plate, and negatively charged molecules drifted toward the positive plate. The charge on the molecules cancelled the charge of the plate, and therefore the cathode rays would not feel any electric force. Even though a lot of air had been pumped out of the cathode ray tube, there were still many air molecules left inside it. Thomson believed that if he could pump more gas out of the tube, the cathode rays would be able to feel the electric force. For this experiment, Thomson designed a special tube. While the cathode was at one end, there was an anode with a hole positioned beside it. In the middle of the tube was a pair of metal plates, one above the other. At the end of the tube, opposite to the cathode, he pasted a ruler. When the tube was turned on, the rays passed through the slit in the anode and between the plates. By looking at the ruler, the position of the fluorescent spot could be measured. Thomson pumped as much gas as possible out of the tube. Then he connected one metal plate to the positive terminal of the battery. He connected the other plate to the negative terminal. Thomson looked at the end of the tube. The fluorescent spot had moved indeed. Thomson did this experiment over and over again. He also used different batteries and different metal plates. Each time he observed a deflection of the cathode rays. From these experiments, Thomson concluded that the cathode rays were streams of negatively charged particles. But what particles were they? Atoms? Molecules? Or something else? If Thomson could find out their mass and electric charge, he would be able to answer this question. The problem was that Thomson could not measure the mass or charge of an individual particle. What he could measure was the deflection of the cathode rays in electric and magnetic fields. From these readings, he could calculate m/E, that is the ratio of mass to electric charge. Since different molecules had different m/E values, the measurement would tell Thomson what sort of particles he had discovered. The result of Thomson's third experiment was that the m/E of the particles constituting cathode rays was about 1000 times smaller than the m/E of a hydrogen ion. At that time, hydrogen ion had the smallest m/E ever measured. Results of Thomson's experiments meant that either the cathode rays carried an enormous charge, or they were amazingly light relative to their charge. The choice between these two possibilities was settled by Philip Lenard. While experimenting on how cathode rays penetrate gases, Lenard showed that if cathode rays were particles, they had to have a very small mass, far smaller than the mass of any atom. The proof was far from conclusive. But experiments by others in the next 2 years yielded an independent measure of the value of the charge of these particles and confirmed the conclusion of Lenard. These developments almost conclusively proved the cathode rays to be made up of tiny negatively charged particles.
Would anything at first sight seem more impractical than a body which is so small that its mass is an insignificant fraction of the mass of an atom of hydrogen, which itself is so small?
Thomson boldly announced, "We have in the cathode rays matter in a new state, a state in which the subdivision of matter is carried very much further than in the ordinary gaseous state. a state in which all matter is of one and the same kind, this matter being the substance from which all the chemical elements are built up. Thomson now came up with 3 hypotheses about cathode rays. Cathode rays are charged particles, which he called corpuscles. These corpuscles are constituents of the atom. These corpuscles are the only constituents of the atom. But not every scientist of that time agreed with Thomson. Especially the second and third hypotheses were hugely controversial. The third, of course, we know, was indeed incorrect. Eventually, scientists accepted Thomson's first and second hypothesis regarding corpuscles or electrons, although with some subtle changes in their meanings. One year after the discovery of the electron, Wilhelm Conrad Roentgen discovered invisible rays that could go through black paper. Since he did not know what they were, he called them X-rays, which are caused by fast-moving electrons. Doctors could use X-rays to take pictures of people's bones. Any program on electrons would be incomplete without a mention of vacuum tubes and the glamorous world of electronics. John Ambrose Fleming, an English physicist, was the first to develop a vacuum tube diode. One of the electrodes, called cathode, emits electrons through thermionic emission, and the other electrode, called anode, which is positively charged, attracts the electrons. The flow of electrons causes a flow of current. The introduction of a third electrode, called grid, between the cathode and the anode by an American engineer called Lee D. Forrest led to a triode, a device which for many years served as a basic tube for amplifying electric signals. The coming of solid-state electronic devices, transistors, integrated circuits, and a host of other miniature components have led to a revolution in electronics. From the tiny microprocessors that control our cars, washing machines, and microwave ovens to the giant supercomputers and sophisticated satellites that link our world through a global network, everything works driven by a constant flow of electrons. Indeed, we owe our present digital age to electrons.